Hello, I am here with the third session actually of quantum computing. Today we're gonna get much more into the how quantum computers works and better understand the mathematical representation of the quantum computers. And here I'm gonna show you also one qubits, like I think it doesn't show properly, but yeah, that I'll show you later, called the Bloch sphere, and we're gonna play around and understand like how we can show the state of a quantum computer just on the light sphere. So you see different state that it can exist there, and we're gonna see it together. More about that. So there's a fundamental change when we move from the quantum computers from the classical computers to quantum computers. So let me bring the pen so you see exactly where I am. So this time we are in the quantum computer, we're not dealing with Boolean algebra. If you remember from the Boolean algebra, we are working with 0 and 1, right? So a transistor is either 0 or in 1 states. That's why we are showing bits. But in quantum computer, we're dealing with linear algebra and we are dealing with vectors. So we're going to multiply a vector by the other vector or multiply a vector by a matrix. So that's a fundamentally different way that we are showing. And why is that? Because the bits actually are kind of like deterministics. Like either you have a low voltage that you have a 0 or you have a high voltage that you have 1. But here in the quantum computers, we are dealing with probability amplitude that I'm going to show you later today. So I explained about it that as Moore's explained back in 60s, so back in 80s, so as we increase the number of transistors, so as we try to shrink the transistors, so we are trying to make them fit within a smaller space. And that's why you see the CPUs that you are using today is much smaller than a CPU that was out there maybe, I don't know, 20 years ago. Let me bring this here. Yeah. But that got a limitation. If you remember that I draw in the previous session. So then, so the number of transistors that can fit within space is keep increasing, but we are hitting a limit. And that's because as transistors shrink to the atomic scale, the insulating layer is actually becoming so thin that the electrons can tunnel through these walls. And that is through the Heisenberg uncertainty principle. And causing current leakage, it causes heat, it causes even bit flip. So you see a lot of unwanted features that are appearing. So quantum tunneling actually makes the classical scaling quite impossible and physically impossible. And now we have to pivot. What if instead of using classical computer, we are not using quantum computer? And Richard Feynman in 1981 said that instead of using classical computer, we have to move to quantum computers because he said like a machine built using quantum computers or quantum laws or quantum physics could simulate nature efficiently because its own state grows at the same exponential rate as the system being simulated. You see, like if you have a plant or a flower outside, they're all using quantum mechanical features to absorb the sunlight and convert that to the energy. So again, as Richard Feynman truly said, the nature is not classical. It is quantum mechanical, and we have to ultimately move to quantum mechanical way of doing stuff. So to make it better and easier for you to understand, if you have n quantum particles, to build that on classical computers, you need 2 to the power of n complex coefficient. So here, if I have again, let's say 100 qubits, If I wanted to do the same simulation on a classical computer, I need 2 to the power of 100 classical bits. And that is more than the number of atoms in the universe. So you see that that doesn't work anymore. And then I need to move on to quantum physics. And now I talked about the classes like P and BQP. By basically BQP is the class that is more of our interest, and that is bounded error quantum polynomial times. These are the problems that quantum computers can solve in polynomial. And the error rates is going to be more than 33%. And actually BQP contain all the P problems. So P is inside BQP classes, or all the classical polynomial time, and some problems in NP also, which means that like integer factorizations can be within BQP, but not all of them. Just have this in mind. So if I wanted to draw it, I would draw here P problems. And here I would have maybe something like that. That is going to be BQP. Sorry, BQ. Maybe better to show it BQP. And some problems of NP going to be also within the same BQP here. That I showed the previous time that how it looks like. If you look at a bit of advancement in this field or the timeline, in 1900 to 1927, it was more like theory discussions. So we had Max Planck, Einstein, Bohr, Heisenberg, Schrödinger, that they discussed the theory and the foundation. Then we go to 1985, that the conversation was more about the universal quantum computer. In 1994, we have the Peter Shores talking about factoring large integers. And 1996, that I'll add it here. 1996, we have Grover that talking about searching through unsorted database with Grover's algorithm. And of course, there are many other algorithms that I'm skipping here. But from 2019 to present, we are more talking about the building quantum computers in the size of 50 to 1,000 qubits. Of course, we've gone more than 1,000 now. But these are mainly like noisy medium scale quantum computers. And now one space that is very important in quantum field is Hilbert space. That is basically just a complete vector space over a complex number. And that's a cube with an inner product, which means that you can't find the inner product of one vector by the other. That I'll show you shortly. So let's move on. And then we have the Dirac notations that we shows a state of quantum with the ket. So for example, here psi, it shows the state of the quantum. And this can be equals to, I'm just representing 1 qubit. So that's going to be alpha state 0 plus beta state 1. And alpha and beta actually are here the amplitude. And they can be a number between 0 and 1. But also there is one condition to also have in mind, and that is alpha squared plus beta squared should be equals to 1. For example, let me make an example. If alpha is 1 over 2, then beta is equals to 1 minus 1 over 4. Beta 2 is equals to that. And that's going to be 3 over 4. So the conclusion of that, beta is equals to square root of 3 divided by 2. So this is how you find, if you have one of the amplitude, you can find the other amplitude. And we have two states here, the grounded state and also the excited state. The grounded state is like the 0, and the excited state is 1 here. And now we can have a duality or dual space that is like kinda instead of kit that we just saw it in the previous slide, this time we are dealing with the bra. And the way that bra works is just transposed and conjugated of the kit. For let me make an example. If your kit is equals to, let's say the kit is equals to a vector here, 1 divided by 2, square root of 3 divided by 2. In that case, your bra will be equals to, here it's just going to be a horizontal. So it's going to be equals to 1 divided by 2, the square root of 3 divided by 2. So you see, I just find the duality for this kit. And if you want to find the inner product, that's also very easy. Let's say you have two states and you want to find the inner products. So let's say if both of them are state 0, which means that they are in the same state, then their inner product is going to be 1. If both of them are in the state 1, their inner product going to be 1. And if they are orthogonal or perpendicular, one of them is in state 0 and the other in the state 1, then the inner product going to be 0. So that's in case that they are orthogonal. So that was about inner product. Also, we have the outer product. Outer product doesn't is quite different because this time we are doing this. You see, for example, if I want to find this, 0 is equals to, I try to show it in the vector presentation. It's going to be 1 and 0. 1 is actually equals to, but no, I'm trying to show the 0 in the broad representation. So 0 gonna be equals to 1 and 0. Now if I multiply these two together, it's gonna be 1, 0 multiplied by 1, 0. So the result 1 by 1 gonna be 1, 1 by 0, 0, 0 by 1 gonna be 0, 0 by 0, 0. So this is the outer product of these two qubits. So alpha and beta, again, they are amplitude. They are not probabilities. Just have this in mind that we need to discuss later on more. And also we have the phase factor. So unlike classical probabilities, amplitude can be negative or complex. Like, for example, your amplitude can be -1 or can be -I or can be I. But this is not possible in a classical computer, right? Because your state is either 0 or 1. We cannot say my bit value is -I. So now if amplitudes can cancel out each other if they are in the destructive interference, and constructive interference means that the amplitude can help each other or can make each other bigger. Like, let's say if I have here two waves, one of them is like this and the other like this. Now, if they are on phase, they can add up together and make it bigger. But if one of the waves is like this and the other is like this, so they destroy each other and the result will be just like a flat line. I talked about this already, but just have in mind again that if you're finding the probability of one of the state, probability of 0 will be alpha square, the square of the absolute value, and the probability of 1 would be absolute value of beta squared. And this condition always is true. Just don't forget about that. Now, qubits can be in the superposition, which means that they can be both in the state 0 and 1 at the same time, which is one of the most powerful features of quantum computers too. And that basically means that you see here, I'll show you better in a better representation later, but they can be both 0 and 1 at the same time. And that is called the superpositions. And now a mixed state is when is like a classical probability, which means that there is no phase relationship and no quantum interference. They are just two separate qubits. And we also can do the tensor products. So if you have two here vectors, vector here, one of them is quantum state 0, one of them is quantum state 1. And they're tensor products. So first you have to multiply 1 by this vector. So let me bring my pointer here. So it would be basically like this. If I want to break it down, it would be 1 multiplied by 0 and 1. And then would be 0 multiplied by 0 and 1. And then we put them all together. 1 by 0 going to be 0. 1 by 1 going to be 1. 0 by 0 going to be 0. 0 by 1 going to be 0. This is the tensor product or Kronecker product. We come up with that later anyway. It's good to just hear it. And unitary matrix is also very important. Every quantum gate, unlike the classical computer, every quantum gate must be represented by a unitary matrix, U. This is not a choice. This is a physical requirements imposed by quantum mechanics. And also there is a mathematical properties. If you multiply the transpose of the unitary matrix by itself, then it gives us the identity matrix. And we have the norm preservation, and also it is reversible. So when I say it's a unitary matrix, means that it is reversible. Let me make an example. Let's say if we have a classical computer like an AND gate that I discussed about it in previous session, this is not reversible. Why? Because if I have this state, let's say 0, 0, 1, 0, 1, 0, 1, 1, the output gonna be 0, 0, 0, 1. Now, if I tell you the output is 0, you cannot tell me what are the inputs, right? Here, because it could be both 0, could be 1, 0 and the other 1, or could be 1, 1 and the other 0. So this is not reversible. So when I say reversible, it means that if I give you the outcome or the output, you can tell me what is the input. And we can also parameterize our qubits. So we can show this state of the quantum qubits with this presentation. Like instead of alpha, I can type right here cosine theta over 2. And instead of beta, I can type here e to the power of I phi here, and then sine theta over 2. And theta is the polar angle. And here we also have the other angle that we can use, or azimuthal angle. But let me show you better in the picture because I know that it's going to be confusing. Okay, now you can see that. You see, this is the angle that you are building with X. I have a pen here. So this is the angle that you are building with this one. So this is this angle. And also if you want to see theta is basically the angle that you are building with this 0 here. So you are building with this 0. And now we have the z-axis. Z-axis is right here. If I want to show you, this is the z-axis. So the top going to be a state 0, the bottom going to be a state 1. Also, we have two more interesting state. One of them is X. That is here. We call this X. And also we have Y state. So this is Y state. I'll talk more about them, but basically this X is also called the plus state. We show them like this, and this is minus. Here should be like that. Yeah, sorry. Let me fix it. It's going to be like that. And also Y here is going to be I and minus I. So this is actually I. And this is minus I. So again, that's like the ball that I showed you here. This is the top. That is the Z plus. And the other side of the ball is Z minus. And also I have X plus here, and I have X minus. And also I have Y plus and also Y minus. So these are the three vectors that you should remember. I'm going to stop here because it's already been half of the slides. I don't want to make this video very long. I'll have a part 2 later, discuss it more. Thank you so much for watching.